All right, folks. Next lesson, the last lesson that we're going to do in electricity is on electrical power and cost of electricity. Just a simple thing. And then I have a worksheet I'm going to post that you guys can type your answers into. Okay. So electrical power is the rate or how fast that electrical energy is produced, used, generated. It's how fast things are happening with regards to energy. It is equal to energy divided by time. If you prefer a triangle, it's energy over time, just like that. As always, I'm going to be going fairly quickly through this. You guys pause it where you need to write things down. It can also be determined that the other way to find power for electrical devices is power equals current. That's I times voltage or potential difference. That's V. So either of these can be used. Maybe I'll just remind you here that energy is measured in joules or capital J. Time has to be in seconds for this to work. And then power is measured in watts. So that unit right there will be new to you. Its symbol is just a capital W. And then, current, just to review, is in amps. Voltage is in volts, and again, power is in watts. So if you have kilowatts or anything like that, you'll have to change it. Anyway, that's kind of the note on it. Other than now we're going to calculate power. So it says a TV is connected to a 120 volt outlet that drawing 1.5 amps of current. Find the power. So for part A, we got to go power equals. And then we think about, well, what do we have? We have voltage and we have current. So it's going to be I times V for this one. Current is 1.5 amps. The voltage is 120 volts, and that's going to equal, I believe, 180 watts. For part B, it says it's left on for 2.5 hours. How much energy was used? So if I look back at that formula with energy in it, it's going to be power times time if you rearrange it properly using algebraic techniques. So now we know that we've got 180 watts, and it's being left on for 2.5 hours. Now remember, I can't have that in seconds. So I take 2.5 hours. If I times it by 60, it gives me minutes. It's 150 minutes. If I times it by 60 again, it gives me seconds. And it is 9,000 seconds. Go ahead and take your calculators out and make sure I did that right. Pause it if you need to. And when I do this multiplication here, I get 162,000 joules. That is 1.62 million. If you want a little scientific notation practice, that's 1.62 times 10 to the power of 1, 2, 3, 4, 5, 6 joules. I would accept this answer either way, though, but 1.62 times 10 to the 6 is good. Is probably the best way to express that answer. Example number 2, a 100 light bulb is connected to a standard outlet. One thing that we should know is that a standard outlet runs on 120 volts. So how much current does it draw? So we go I equals power over voltage. The power is 100 watts here. I just rearranged the formula. Over 120 volts. 100 divided by 120, 0.83 amps of current. I think you'll find this is a lot easier to play around with than solving circuits from last week. So that's about as tough as these power questions are going to get. There's this version of the formula, and then there's the other version, which was power equals energy over time. So as long as you can handle using those, you should be just fine. So now we're going to look at that power and convert it into cost of electricity. Again, I'm going to be going too fast for you to keep up writing, so pause it when you need to. We get charged for energy, not power. That's what's sold by the electric companies. So you can calculate the energy used by rearranging our equation. And it's going to give us energy equals power times time. But a joule is a really small amount of energy, so we use larger units. Instead of the power being in watts, we put it in kilowatts. And instead of the time being in seconds, we put it in hours. And that'll give us an energy unit that's weird to most physicists anyway, which is kilowatt hours instead of joules. If you've ever seen an electricity bill before, you'll notice that it's charging you in kilowatt hours, not joules of energy. So what do we do? Well, my PowerPoint's a little dated. Nobody pays 8.5 cents per kilowatt hour anymore. Let's say it's about 13 cents per kilowatt hour. Nowadays that we have smart meters, there's a time of use thing, which is fairly new, really. We got our smart meter within the last 10 years, and basically it charges you different amounts of money depending on the time of day. So I'm going to use 13 cents, which I think is kind of around the medium amount that we pay. A 60-watt bulb for 30 minutes. Well, how much money does that cost if it's 13 cents per kilowatt hour? So you go energy equals power times time. But we need the power in kilowatts. Well, what is 60 watts in kilowatts? Well, that's easy. Just divide it by 1,000. So I go 60 divided by 1,000 on my calculator, and it's 0.06 kilowatts. 30 minutes is not an hour. How many hours is it? It is half an hour. So I'm going to write in 0.5 hours. So this is going to tell me how much energy we consume. 0.06 times 0.5 is 0.03 kilowatt hours. Very little energy. 160-watt bulb on for 30 minutes doesn't consume very much energy. To find the cost, though, which is what we end up wanting to do, you take your energy and you multiply it by the rate. The rate is given in the question. That's the 13 cents per kilowatt hour. So in this case, you're going to end up typing in 0.03 kilowatt hours times 13 cents per kilowatt hour. That is what you got. 0.03 times 13 cents. This is 0.39 cents. That's how much it costs. Not very much money. And you might think, what's the big deal then? Why not leave some lights on here and there? The problem is we have so many little lights that consume energy in our homes that it ends up adding up. There's so many of these things that use energy. What I'm doing right now is using a lot more energy than a 60-watt bulb. So 0.39 cents would be the cost there. And I think I'm probably going to have to erase this. I'm assuming there's a part B that's going to encroach on this. Maybe I'll get away with it. Let's see. So again, energy equals power times time, but in this problem, they don't give me the power, like 60 watts in the last one. So I'm going to start by finding the power. It's V times I, or I guess technically the formula said I times V, but you guys should know by now that that doesn't matter. I times V is the same as V times I. So I'm going to go 1.3 amps times 120 volts. 1.3 times 120, and it gives me 156 watts, 156 watts. Now I want that in kilowatts divided by 1,000. It'll be 0.156 kilowatts. All right, so that gets me to that point from the last question. So a little bit of a slower start. Let's see if I can get this in here. So my energy consumption is equal to 0.156 kilowatts times 1.5 hours. 0.156 times 1.5. It gives me 0.234 kilowatt hours. That's what it gives me there. Now that doesn't give me the cost again. You might notice though that I did use more energy in whatever the heck this is compared to the first thing. This might be something like a TV. So I'm going to write over here cost equals, again, energy times my rate. So 0.234 kilowatt hours times 13 cents per kilowatt hour. Got a little messy there. 0.234 times 13 cents gives me 3. So I got about, cost me about 3 cents to run that thing for 1.5 hours, whatever it was. More than the first thing costs, and that's the way that goes. Lots of these little things adding up in our homes. So anyway, that is the lesson. What I want you to do is try and complete the questions as best you can right in the document. If there's something where you have to show a little bit more work, go ahead and do it on paper, and then just take a picture with your phone or tablet or whatever, and you can insert that picture right into the document. And I'll mark that and get it back to you as quick as I can. Your assessment for this part of your final assessment, really, for this electricity stuff, it's only going to be based on what we've done since March break. So it's going to have what's that? It starts with Kirchhoff's laws, the voltage loop rule, the current loop rule, the current junction rule, rather, adding resistances in series and parallel, and then solving circuits. The 3 circuits that you're going to have to solve on this assessment is there's going to be one just easy series circuit, one simple parallel circuit, and then one and only one combination circuit. I'm even considering using just 3 of the ones I've already had you do, like the 6 from last week, because well, then everybody that's completed those questions will get perfect. I guess that's something, or at least make them similar so that you know what to do, and it's just a matter of can you figure it out from there. And then I'm going to have a couple of these power and cost problems, which this should be easy. This is stuff that you should just knock right out of the park, and you'll have no problem whatsoever with that. Okay, so that's going to be your assessment. I'm going to post it. I'm going to give you a couple of days to go over this, and then I'm going to post that assessment on Wednesday, and it'll be due Friday. Right? It's not technically a test because it's open book, and you've got 3 days to do it. But I'm going to count it as the test for this part of the chapter, and then next Monday we can start in chemistry. All right, that's all for now, guys. Good luck.